This is the 19th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses signed arithmetic. In the last video, we learned how to represent signed integers in hardware using an encoding called 2's complement. We also discussed the benefits of this encoding over other options like signed magnitude. So let's just jump right in. How do you convert your unsigned adder into a signed adder? In other words, what changes do you need to make to your unsigned adder in order for it to add signed numbers encoded using 2's complement? Well, none. Remember, we designed 2's complement specifically so that the existing adders would just work. But, oh wait, there's an asterisk. It turns out that there's one thing we need to address. Overflow. With an unsigned adder, carry out indicates overflow. For example, consider this 4-bit unsigned addition. When we add 12 and 10, the answer, 22, is outside the range for a 4-bit unsigned number. The adder will indicate this by putting a 1 on the carry out, in some sense signaling the need for a 5th bit to represent the output. However, when doing signed addition, the presence of a carry out does not necessarily indicate overflow. For example, consider adding -1 and 1. There is a carry out, but this addition doesn't result in an overflow because the sum is 0, which is within the range of a 4-bit signed integer. Similarly, there can be overflow even if there's no carry out. Consider adding 5 and 7. The sum is 12, which is not in the range of a 4-bit signed integer. Thus, this is an overflow even though the carry out is 0. Now this result could be confusing at first because the adder produces 1100, which at a glance looks like 12, but remember, we should interpret the input and the output the same way. Because we interpreted 5 and 7 as signed integers, then we should also interpret the output as a signed integer. 1100 as a signed integer is -4, not 12. One part of Project 1 is to figure out how to detect overflow in a signed adder. Detecting overflow is important because, as you can see in this example, when there's overflow, the output may be wrong. Or is it really wrong? How do we know if we're supposed to interpret the arithmetic here as unsigned 5 plus unsigned 7 equals 12, or as signed 5 plus signed 7 equals -4, which is an overflow? Well, they're both potentially correct. Remember in the last video when I said that there's nothing inherent in a bit string that tells you if it's binary or 2's complement. This right here is the consequence of that. The meaning of the output depends only on how you choose to interpret it. And in practice, the way we're choosing to interpret the output usually depends on the context of the problem we're solving. For example, are we working on a part of C code that's using regular ints or unsigned ints? Now remember, you need to decide how you're going to interpret the bits before you see the answer. So if you commit to interpreting the output as a signed number, you have to interpret it as -4, in which case you're relying on the overflow logic to alert you to a problem. I have a feeling this is still a little bit unclear, but that's okay. Keep thinking about it, and we'll revisit this idea again when we begin building a CPU and have some more context. Now that we can add both positive and negative numbers, what about subtraction? Well, we more or less get subtraction for free. To see how, take a minute and rewrite a minus b as an addition expression. We can rewrite a minus b as a plus -b. Thus, to subtract, we just need to negate b and use our existing adder. Oh, damn it, there's that asterisk again. Okay, so there is one caveat. Notice that we can't negate the most negative number. For example, when using a 4-bit signed adder, we can't negate -8 because +8 is out of range. To work around this problem, you'll need to make use of the adder's carry in. You'll also find that using the carry in will help you do the negation more efficiently. I'm being intentionally vague about the negation here because figuring out the details is one of your tasks in Project 2. But I will give you one hint. Think about the shortcuts presented in the last video. One of those shortcuts can be implemented in a very straightforward manner in hardware. So now let's see how to build a single circuit that both adds and subtracts. This circuit will take 3 inputs, the 2 numbers to be added or subtracted, and an op input, short for operation, that specifies whether to add or subtract. So let me first show you the simple but wrong way to do it. And in this case, by wrong, I mean suboptimal, not broken. It'll work, we just don't want to do it this way. I'm just showing it first because it's a little easier to follow. The basic idea is that you send inputs A and B to both an adder and a subtractor, and then use a mux to select which answer you want. If the op is 0, the output is the result of the addition, and if the op is 1, then the output is the result of a subtraction. Now this must initially strike you as wasteful. We're performing two calculations even though we know we're always going to throw one out. But this is in fact how many CPUs are designed even today, although we're slowly moving away from that for energy reasons. It turns out, however, in this specific case we can do better. We can put the mux and some of the other logic before the adder so that the circuit only uses one adder instead of two. Instead of doing both addition and subtraction and then throwing one out, the technique here is to cleverly manipulate input B so that the one and only adder in this circuit performs the desired calculation, either addition or subtraction. We can't always do that, but we can here. To be clear, for project 2, you should not have a separate adder and subtractor. You should use this design here. Another constraint that you should see in the instructions is that this selector logic should not have an adder in it. That's against the rules. You need to figure out how to use the adder's carry in place of where you might be tempted to use an additional adder. Okay, so based on this video, you should be able to design and explain a circuit that detects overflow in a signed adder. You should also be able to design and explain a circuit that negates an integer. And you should be able to design and explain a subtractor. In the next video, we'll look at Boolean algebra and how we can use that to find a more efficient way to implement a 2-to-1 mux.